Okay, welcome back. This is 9.1, working with sequences. So this is just an introduction to sequences. The type of sequences that we'll be interested in will be sequences of partial sums, because we'll be able to use those things as approximations of functions. So you may remember tangent line approximations. So recall, hopefully this is not too far off topic, but recall tangent line approximation of a particular point on a function. So maybe we had a tangent line to that point right there at some value c. We could say, given this point is c comma f of c, we can approximate the function f of x in a particular interval around c with the tangent line, where the tangent line will be defined as f of c plus f prime of c times x minus c. Okay. It turns out later that we can extend this definition to not just tangent lines, but tangent polynomials, so to speak. And we'll call those later the Maclaurin or the Taylor polynomials. And they'll have higher degrees, but in general, there'll be a sum of things. So it'll be some constant plus the derivative times x minus c plus f double prime of x minus c, f double prime of c times x minus c squared plus f triple prime of c times x minus c cubed. And then there's also this little constant issue going on and down below. But what it is a sum of things. Okay? It's a sum of some constant, which we'll have a formula for eventually, but let's just call it a sub n times x minus c to the nth power, n equals 1 to whatever degree of polynomial that you're worried about. So, I don't know. We're going to be interested in sequences, but in particular sequences of partial sums. So this thing can be seen as a sequence of partial sums. You can think of it as the first term is f of c. The second term then is f of c plus f prime of x minus c. F prime of c times x minus c. Then the third term would be f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared, etc. So you'd have a sequence of things, partial sums basically, and we worry about whether or not these go somewhere. In other words, converge to some value. Okay, so eventually that's where we're headed. Okay. We want to first investigate sequences in general and build some tools that will allow us to deal with these things later on, which become sequences of approximating polynomials, I guess you could put it that way. Okay. So that's where we're headed, and let's dive in here. So 9.1, we're talking about sequences. Section 1, we just want to define what is a sequence. It's basically a function, but it has a restricted domain. We restrict the domain to the set of positive integers. Okay. So any function we've already worked with can be thought of as a sequence. For example, y equals 3x plus 1. Okay. you could think of as a sequence just by considering the domain X, let's write domain D, to be the numbers from 1 to infinity. Okay? So in that case, the output of this function will be, well, if I put in 1, I get 3 plus 1, which is 4, sorry. If I plug in 2, I get 6 plus 1 is 7. If I plug in 3, I get 9 plus 1 is 10, and so on and so forth. We're used to thinking of this thing as maybe the equation of a line, right, in the xy plane. So we would never want to list out all of these values, all the real values, because there's just millions and kabillions of them, right? We would plot it instead. So up 3 over 1, and we would have this picture. Now what we're saying is we're just going to look at the integer values. So you get a bunch of dots as opposed to a straight line. And these things then are the terms of the sequence. We'll give them names. So in general, we're no longer going to use y's and x's. Okay, so instead of using y's and x's, now what we're going to do is rewrite something like this as a sub n equals 3n plus 1. Okay, where you can think of this as a of n. Okay, so the function, instead of f of x, so maybe before this would have been f of x equals 3x plus 1. Instead of x, we're using n's. Instead of f or g or h or something like that, we're going to use a's, b's, and c's. Okay. And then instead of using this function notation where we have parentheses, we're going to use subscripts. Okay, so a sub n. But this is going to be our nth term formula for the sequence. Okay, so the first term, so a of 1, or a sub 1 if you'd rather, you plug 1 into here, you get 3 plus 1 is 4. That's called the first term. And then a sub 2, you plug 2 in there, you get 6 plus 1 is 7. That's the second term. And so on and so forth. And you could talk about general terms. Let's say a sub I will be 3i plus 1. That will be called the ith term. Okay. To talk about the entire sort of range, or the entire sequence for us, we'll use these curly brackets. So the entire sequence then will designate curly bracket a sub n. And sometimes they'll tell you where you start over here, and then so it's a little like an integral, you know, from n equals 1 to infinity. Okay, but our book doesn't use that notation. Okay. So the first couple problems will just have you list out terms of sequences. So one kind of function that you don't see in the real numbers that you do see now with sequences will be this -1 to the n thing. But anyways, write the first 5 terms. So problem 2, a sub n is -2/5 to the n. I'm going to rewrite this, okay? And you'll get a lot more practice with exponents in this section. You could rewrite -2/5 as -1 times 2/5 to the n. And then you could distribute this power to each term, right? So you can think of -1 as -1 to the first power, and then just multiply the exponents, and you end up with -1 to the nth times 2/5 to the nth. And then to write out the first 5 terms, you're just plugging 1 in for n. So -1 to the first power times 2/5 to the first. Negative to an odd power is negative, so this would be negative 2/5. And a sub 2, negative 1 squared times 2/5 squared. This time a negative to an even is positive, so you get 4/25. This one's negative. This one's positive. Oops. And then finally, the fifth one is negative. Okay. So every once in a while, you'll be called upon to generate a formula or produce a formula that will give you negatives on the odds and positives on the evens. And in that case, your formula a sub n will be negative 1 to the n times whatever. Okay. So in this case, we had 2/5 to the n as our whatever. So this gives me even terms positive. But if you want the even terms to be negative, you're going to use negative 1 to the n plus 1. And that will give you even terms positive. Okay. You could also use negative 1 to the n minus 1 for even terms positive, but we'll just keep it as is. Whoops, the even terms negative. Right? Because in this case, the exponent will be even when n is even, and in those cases it'll be positive. So negative to an even will be positive. In these cases, you'll have an even number plus 1 will be odd, so you have a negative to an odd whenever it's even, and therefore it'll be negative. Okay, eventually we'll want to know what happens as we take this to infinity, because we're, like I said, we're going to be using these things for approximations, and they're only useful if they actually converge to some sort of limit. Okay. So again, we'll have the strict definition of a limit that you saw back in Calc 1. If you went on to take advanced calculus, you would sort of start in this context and then derive everything that you know about continuity and limits of functions from the limits of sequences. So it's a very important thing if you're continuing on in math. Most of us aren't, though, so I'll just note the definition. The limit, well, a lot of the proofs in this section are going to be dependent on the strict definition. So I don't want to say that we shouldn't know the strict definition, because if you don't know the strict definition, you're bound to get lost in all the proofs. Okay? If you don't understand sort of the mechanics or the proofs of everything, then it just comes down to you sitting there memorizing everything by rote, and it's just a terrible way to remember things, in my opinion. So if you know the mechanics, it'll help a lot. So yeah, I'm not going to say don't bother with this unless you're going to go on to become the next Good Will Hunting, but I think it is kind of important for us as students, even at this elementary level. Okay, so strict definition of a limit. The limit of a sequence a sub n is L, which is written as the limit as n goes to infinity. And we only care about n going to infinity. So it's what happens in the long run as we keep going a5, a6, a7, a100, a2000, a2 million. That's what we're worried about. So the limit of a sub n equals L if for every epsilon greater than 0, there exists some big N value greater than 0 such that if N is greater than this big N, then the A sub N terms will be really, really close to this L value. Okay, in other words, the difference between A sub N and L will be less than epsilon. If this limit exists, we say it's convergent. If not, we say it's divergent. Okay, so if the limit as N goes to infinity of A sub N exists, we say it's convergent. And if not, we say it's divergent. Okay. So we'll be using these sequences of partial sums eventually to do approximations. We might not necessarily care about the ultimate limit. We just want to know if the limit exists. Because if the limit exists, we can use kind of the beginning values to do the approximation. We don't necessarily have to have the ultimate limit. And a lot of these tools that we'll learn in the next upcoming 5 or 6 sections will be about just figuring out if the limit exists. So we won't care what the limit is, just does the limit exist? And then we'll go from there. Okay. Finding limits of sequences then. So it turns out that you can use all your calculus rules. And the only difference here is we have an n instead of x. Technically, there's kind of issues of continuity. Okay. Because obviously a sequence is a bunch of dots and when you look at the graph. So it's not a continuous function. It's not something you can draw without picking up your pen. So there's issues there, but you could use, it turns out the rules that you learned in calculus are more powerful than they supersede the limit of a sequence. So if the limit of the function is equal to L, you know automatically the limit of the sequence is also equal to L. Okay, okay, so problem 30, we have A sub n equals 8 plus 5 over n. So if we were working in Calc 1, the corresponding question would be, what is the limit as x goes to infinity of 8 plus 5 over x? So as x goes to infinity, this thing will go to 0, and 8, the limit of 8 is just a constant, so this will just be 8. So what does that tell me? That tells me if this is 8, it means that the limit of the sequence as n goes to infinity is also 8. Okay. So technically you're supposed to do your work in terms of x and then make this conclusion. From this point on, though, I think I would rather just take that as an assumption, and when I do my limits, I'll be using the letter n as opposed to x. So it becomes particularly important, I think, for doing L'Hopital's rule. Technically, you can't do L'Hopital's unless the thing is continuous. If it was not continuous, it would not be differentiable. So problem 35 is kind of probably what I would consider the reason why you need to do this technical step here. Okay, so we're trying to find the limit of this thing as n goes to infinity. If you were working in x, and for this problem I will work in x, just to try to drive home the fact that this would only work if the function was continuous. We would have ln of x cubed all over 2x. And if you look at the form, ln of something going to infinity will go to infinity. 2 times something going to infinity would be infinity. It's infinity over infinity. So you do L'Hopital's. What do we get? X cubed, 1 over x cubed times 3x squared all over 2. This would be the limit as x goes to infinity of 3 all over 2x, and then that would be 0. Okay, so then the limit as n goes to infinity of ln of n cubed all over 2n must be 0. Okay, so clearly, in order to do L'Hopital's rule, I need to have that the differentiability of these functions. Okay. So I mean, I don't know. It's literally, I have to go back and look at the criteria for L'Hopital's, but I presume that you would need some sort of differentiability. In order to have something be differentiable, it's got to at least be continuous, right? So if it's not continuous, it's definitely not differentiable. If it is continuous, it may or may not be differentiable, but if it's not differentiable, so I'm losing myself. If it's how did that go? If it's continuous, if it's differentiable, then it's continuous. If it's not continuous, it's not differentiable. So I don't know. But anyways, it's just a technical issue. I'll disregard it in the future, though. I'll always be writing my limits in terms of n. Long story short. Okay. Showing that a limit does not exist, back in Calc 1, you would have to kind of show that there was subsequences. If the limit did not exist, there were certain types, there were certain ways it didn't exist. It was because of oscillation, because of unbounded behavior, and because of different left and right-handed limits, right? Those would be the cases where the limit did not exist. Here, in particular, we'll use often the fact that the limit of there's kind of an oscillation behavior. In other words, if the limit of the even terms of the sequence do not equal the limit of the odd terms of the sequence, then you can conclude that the limit of a sub n does not exist. It turns out the other direction will be true. If the limit of a sub n exists, then you can conclude that the limit of the even terms must equal the limit of the odd terms. Okay. So sometimes that's a valuable piece of information, but this one will sort of get us through the problems that we're encountering in the book right now. 31, we have a sub n is given as -1 to the n times n over n plus 1. So we want to know the limit of this sequence as n goes to infinity, and we can investigate it just by looking at some of the terms, right? So a sub 1 is -1 times 1 all over 3. A sub 2 is +1 times 2 all over 3. This should be 1 over 2. A sub 3 is -1 times 3 all over 4, etc. Right? So what's going on is I have negative term here and here, negatives on the odds and positives on the even. Okay, so if we consider kind of the even terms, which we could give by using the formula negative, or rather the even terms are all positive, right? So we could say the even formula would be just plain old n over n plus 1, where the domain that we're putting into this function are even numbers. And then the odd guys would be -1 times n all over n plus 1. And then consider those limits. So the limit of n all over n plus 1 is +1 as n goes to infinity. The limit of the odds is negative n all over n plus 1, which is negative 1 as n goes to infinity. Okay, so the limit of the evens does not equal the limit of the odds, and therefore the limit does not exist. It has oscillating behavior. So we could say the sequence diverges. Okay. The squeeze theorem we saw from in Calc 1, we see it again here. So 43, we have the formula a sub n equals sine of n all over n. So we can find the limit by sort of considering this inequality. Sine of n is always going to be bounded in between -1 and 1 for any n. Then we can divide all three sides by n, supposing that n is greater than 0. And then we could take the limit of these these two sides here. And if the limit of these two sides is equal to the same thing, it forces this limit to be equal to that. That's the squeeze theorem, right? So we note the limit of -1 over n is just equal to 0 as n goes to infinity. And then the limit as n goes to infinity of 1 over n is also equal to 0. Okay. So by the squeeze, the limit of this inner part will also be equal to 0. So the limit as n goes to infinity of sine of n all over n is equal to 0. Okay. Using the squeeze theorem, you can prove some other theorems. One theorem that we always forget about later on is the absolute value theorem. Don't use it very much, but when you do, by the time you do, you kind of have already forgotten about it. And it basically says if the limit of the absolute value of the terms of the sequence is 0, then the limit of the original sequence is 0 as well. The proof is definitely worth looking at. It's kind of a cool proof. And it follows from a very simple fact, the fact that a sub n is greater than or equal to negative absolute value of a sub n, which is less than or equal to the absolute value of a sub n. And then we could use the squeeze theorem. So we're supposing this is true. The limit of the absolute value of a sub n equals 0 as n goes to infinity. Supposing that's true, we can evaluate the limits of these two sides. So we note the limit of negative absolute value of a sub n as n goes to infinity will be just negative limit of the absolute value of a sub n as n goes to infinity. Of course, it would be -1 times 0, which is 0. And then on the other side, of course, the limit of the absolute value of a sub n is 0. So by the squeeze theorem, the limit of the middle guy is also 0. Okay, so a clever little proof dependent on this fact. So this is like one of those gateway facts that you can use to unlock proofs. So it reminds me of the fact that sine of n is in between -1 and 1. It's that same kind of idea. Okay, so let's look at number 12, where we apply the absolute value theorem. We want to know the limit of a sub n, which equals -1 to the n all over n. So we can consider then the absolute value of that expression. The absolute value of a sub n, well, in this sequence, it's odd terms are going to be negative, the even terms will be positive. But if you take the absolute value of each individual term, all the terms will be positive. So it turns out this -1 to the n does not affect anything. Okay, so the actual expression for the absolute value of a sub n will just be 1 all over n. If you don't believe me, write out this and then write out this for the first 5 or 6 terms and see, the truth of it. Okay, but once we get this expression, we know how to figure out that limit. The limit as n goes to infinity of the absolute value of a sub n, which I'm telling you is just 1 over n, that's equal to 0. Okay, so that tells me that the limit of plain old a sub n, which is -1 to the n over n, is also 0. So when you take absolute values, you kind of can kick out all these -1 to the n's. So maybe a crazy example, a sub n equals -1 to the n plus 1 times, I don't know, n plus 1 factorial all over -1 to the n times n factorial times 3 to the n. Okay, so that ugly thing. The absolute value of a sub n, the absolute value of this thing, will just be the same thing, but without all these -1 to the n's. So you'll just end up with n plus 1 factorial all over n factorial times 3 to the n. So these -1s, the only effect it will have is changing the individual terms of the sequence to either a negative or a positive. If you take the absolute value of the individual terms, they're always going to be positive. So it kind of has an effect of canceling out these -1 to the n's. Okay. The last thing in here is kind of a technical thing, and again, it's not like something that you'll never see again. It's used in the proofs of the theorems that are coming up. And so what is it? It's this idea that if a sequence is bounded and just increasing or just decreasing all the time, then it'll be automatically convergent. Okay. So section 5, if you can prove that something is monotonic, and then you can also prove that the thing is bounded. So monotonic means it's always increasing or it's always decreasing. That'll mean it's convergent. Okay, so we'll need to work with monotonic proofs later on in this chapter. So I'm going to show you some proofs for proving things are monotonic. Boundedness is kind of, I just consider it kind of an obvious type quality. So I won't go too in depth with that. We'll say, then putting it all together, there's kind of a proof for all of this that we want to look at as well. Okay. And I'm curious whether I should do the proof first. Yeah, sure. Let's do the proof first. In order to do the proof, I want to remind you again of the definition of a convergent sequence, the strict definition. So we say the limit as n goes to infinity of a sub n equals L if for every epsilon greater than 0 there exists an n or maybe an m greater than 0 such that if little n is greater than big N, then the distance between a sub n and L will be less than epsilon. Okay, so in our proof, we're trying to kind of obtain this statement. We're given that the thing is monotonic and bounded. Okay. So we're supposing a sequence of numbers is monotonic and bounded. Okay. In particular, let's presume the thing is increasing. So the sequence a sub n is increasing. So we can look at the sequence, then consider it. So we'll have a sub 1, and because it's increasing, a sub 1 will be less than or equal to a sub 2, which will be less than or equal to a sub 3, which would be less than or equal to a sub 4, which would be less than or equal to dot, 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 which is less than or equal to a sub n, which is less than or equal to dot, dot, dot. And then it's bounded above, okay, so it's monotonic and it's bounded. Okay, so it's bounded above, so we could say dot, 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 it's less than or equal to some number we'll call m. Or maybe we should call it m. So I'm going to use the letter m later. Okay, there's another fact from math that you probably aren't as familiar with. If a set of numbers is bounded above, there exists this special number which is the smallest of all of these bounds. Okay? So we call it the least upper bound. And that's because of this thing called the Completeness Axiom. So from the Completeness Axiom, if I had the set of all numbers that bounded the sequence above, that set of numbers would have a minimum, okay? And that thing would be the least upper bound. And we could give that then a name, L. So therefore, L will be less than or equal to whatever the heck this thing is, M. And we could rewrite this expression with an L over there instead. One extra bit of information is if we take anything less than L, it will no longer be a maximum, a least upper bound type. Because if you go less than L, you've assumed that L was the least upper bound. So if you have something less than L, it can't be the least upper bound. Okay, because that would imply that it would be the least upper bound. So what? If we take an epsilon greater than 0, and note L minus epsilon is greater than, sorry, would be less than L. So E, epsilon, this little E looking thing is just some small number. Okay, this thing is no longer an upper bound of this sequence of numbers, and therefore there must be other terms of this sequence which go above this thing. Okay. If not, then that's kind of what I was getting at before. I probably butchered that statement, but if there weren't any terms a sub n greater than L minus epsilon, then L minus epsilon would end up being the least upper bound, which is a contradiction because we've said that L is the least upper bound. So there must be terms, say a sub capital N, such that a sub capital N would be greater than this L minus epsilon. And that'll be true for all little n greater than this capital N. Okay, because it's an increasing sequence, the next number in the sequence will be bigger than this, which will be bigger than this. Okay, so there must be terms a sub n such that a sub n is greater than this, and all n greater than big sub n will in turn fulfill that inequality. Okay. And kind of what we're doing is building this strict definition. Right? So it's all there, you just kind of have to piece it together. We note that L is in between L minus epsilon and L plus epsilon. Okay. Furthermore, we can say, and what I'm trying to do now is produce this inequality right here. I'm kind of not doing a very good job of it, but that's what I'm after. So we have this fact, but from this fact, we can also say that L minus epsilon is less than A sub n, which is less than L plus epsilon. We have this fact from before, but this is obviously true as well because A sub n is bounded above by L. So A sub n is definitely also bounded above by L plus epsilon. We could subtract L from all three sides of this inequality, and then we get A sub n minus L less than epsilon. And then we could rewrite that as an absolute value. So we'll say the absolute value of A sub n minus L will be less than epsilon. Right? And then we kind of have it. So this will be true for any n greater than big N. So for, and then we said epsilon must have been arbitrary. So for any epsilon, I guess I didn't explicitly say that, but I meant it. Okay, so for any epsilon greater than 0, there will exist this n value greater than 0 such that for all little n greater than big N, A sub n minus L will be less than epsilon. In other words, the limit of as n goes to infinity of A sub n will equal L. Okay, so it's a clever proof. One probably new concept is this completeness axiom, but it's pretty simple. It just means if you have a set of numbers and you know the set of numbers is bounded above, there's going to be this smallest number from the set that bounds the set above. Okay? And that smallest number does not necessarily need to be in the set. I should clarify that. I want to go to your book for the explicit definition. Okay? There's also greatest lower bounds on the other end of things, and I presume you would use that for the proof of the other type of monotonic sequence, the decreasing types. Okay, so anyways, there's that. It's in the book if you want to take a closer look. I know I butchered it a little bit. So let's get back to what we're working with. We need to do proofs on monotonicity and proofs for boundedness. And then if you have both of those together, you'll have convergence. Okay. So monotonicity proofs we'll need again later on in this chapter. So I need to take some time rehearsing those. So monotonic proofs. And we have increasing types and decreasing. Some books will say strictly increasing, strictly decreasing. There's a couple issues that we need to work around. For example, a sequence that doesn't increase or doesn't increase, it just stays the same all the way out. Is that increasing or is that decreasing? I don't know. So they would say strictly increasing if it's never equal to itself. But just in general, we'll say increasing means a sub 1 is less than or equal to a sub 2 is less than or equal to dot dot dot, less than or equal to a sub n, which is less than or equal to a sub n plus 1, less than or equal to dot dot dot. Then decreasing is the reverse, right? So a sub 1 greater than or equal to a sub 2 greater than or equal to dot greater than or equal to a sub n greater than or equal to a sub n plus 1 greater than or equal to dot dot dot. Okay. So the book, to get around this issue of whether or not it's going up or down or it's always staying the same, they have decided to call this, as opposed to increasing, they're calling it non-decreasing. Okay? So it can be remaining constant, is what the book is saying. And then instead of saying decreasing, they're going to say non-increasing, which is a headache, but there's no way to get around it unless you introduce extra definitions. Okay, so there's the proofs hinge on this part of the inequality right here, and then this part of the inequality. At least the algebraic proofs do. Okay, so there's actually two types of proofs. The algebraic types, and then the calculus types, where you look at the derivative of the corresponding function to the sequence. So the algebraic proofs are hinging on these kind of facts. So we could say increasing, or in this case, non-decreasing proofs. And then we also have non-increasing proofs. And so for non-decreasing, you want to show one of the following things. You want to prove that a sub n is less than or equal to a sub n plus 1. Or you want to prove that a sub n plus 1 minus a sub n is greater than or equal to 0. Or you want to prove that a sub n plus 1 divided by a sub n is greater than or equal to 1. Okay, so it's just by manipulating this original inequality that I get these other types of proofs. So for non-increasing, it's just a reversal of the inequality type. And then calculus, you take a look at the derivative of the corresponding function to the sequence. Okay, so I'll just write f prime of n, where I'm assuming it's in terms of x, but just to remind you that this f of x is equal to a sub n at the integers. Okay. So if you take the derivative and you find that's greater than or equal to 0, it's non-decreasing. If you take the derivative and find it's less than or equal to 0, it's non-increasing. Okay, so let's go through and look at these types of proofs in context. Problem 54. A sub n equals 3n all over n plus 2. Okay, so I don't know if it's increasing or decreasing, or non-decreasing, non-increasing yet. So what you do is kind of investigate this expression and see if is it greater than or is it less than 0. If it's greater than, it's not increasing, or sorry, not decreasing. If it's less than, it's not increasing. Okay, so let's consider a sub n plus 1 minus a sub n. So what is a sub n plus 1? First off, maybe that's a good question. Well, you're going to replace n with n plus 1. So wherever I saw an n in this expression, I replace it with an n plus 1 in this expression. That'll give me 3n plus 3 all over n plus 3. Okay, so a sub n plus 1 minus a sub n is equal to this thing minus this thing. I'm going to find a common denominator. So multiply top and bottom of this thing by n plus 2. So 3n squared plus 6n plus 3n plus 6. Then subtract away, need to multiply top and bottom of this thing by n plus 3. So that would be 3n squared plus 9n. That's all over n plus 3 times n plus 2. Okay, so 3n squared minus 3n squared is 0, n squared. Then I have 6n minus 9n is minus 3n. And then I just have the crud, there's another 3. So 6n plus 3n minus 9n is 0 n's. And then I just have 6 all over n plus 3 times n plus 2. And I want to compare that to 0 for values of n. And because we're going to infinity, you can pick n values greater than 1, greater than 2, greater than 3, just so long as eventually it stays either above or below 0. So I'll say for n greater than or equal to 1, for instance. So if I plug any n value greater than or equal to 1 into this expression, the numerator will be positive, the denominator will also be positive. Positive divided by a positive is positive. Positive is greater than 0. Okay. So I go back to my chart, that's this case, and so we say it's non-decreasing. In this case, it's actually strictly increasing, but just to be consistent with the book, we'll say non-decreasing. In other words, it's increasing. Okay, let's get another one. This is 57. We have a sub n is 2/3 to the n. This time I'll consider a sub n plus 1 all over a sub n and compare that to 1. So again, what is a sub n plus 1? That's 2/3 to the n plus 1. So a sub n plus 1 over a sub n is 2/3 to the n plus 1 all over 2/3 to the n. Rules of exponents say subtract exponents, so I have 2/3 to the n plus 1 minus n. In other words, 2/3 to the 1, which is 2/3. And then you compare that to 1. Okay? That thing is less than 1, so that tells us it's non-increasing. Let's get one more type, 55. A sub n equals n e to the negative n over 2. This time I'll do the calculus version, so I consider f of x equals x e to the negative x over 2 and take its derivative. I want to set it equal to 0. I'll factor out e to the negative x over 2. This will never equal 0, so I just consider this part. So I'll have x over 2 equals 1, and so x equals 2 is my critical number. Okay, I'm just going to consider the values then that are greater than 2, because then the sign of the derivative won't change. So for x greater than or equal to 2, f prime of x will equal, well, when you plug in, for instance, and I guess we want to go just strictly greater than 2, not greater than or equal to, sorry. So for values greater than 2, if I plug in, for instance, 3, I'll have 1 minus 3 halves. 1 minus 3 halves is 2 halves minus 3 halves, which is negative. So this derivative will be less than 0. In other words, it's decreasing. In other words, it's non-increasing for values of n greater than 2. Okay, so once you're able to show that something is monotonic, and we'll be working with monotonicity later on in the chapter again, so I'm reminding you we need these types of proofs later on. Once you have those types of proofs under your belt, you want also to check boundedness issues. I'm sort of lost as to what number I'm on. I'll just say part C, boundedness. And I'm saying it's kind of obvious as to how these things are bounded. So, for instance, this guy, we already know that the thing is, from before, we know the thing is non-increasing. In other words, it's decreasing. So we want to show it's bounded below. And if you think about the terms of the sequence, so a sub 1 is 2/3, a sub 2 is 4/9, a sub 3 is 8/27. They'll never be negative. So it's bounded, definitely bounded below by -5. So it's bounded below. It's definitely bounded. It has at least a greatest lower bound of 0. Okay? But you don't need to go there. You just need the greatest lower bound for the proof. Right? So we just need to show it's bounded below somewhere. So I can do that just saying it's bounded below by -5. I think that's obvious. And then secondly, from our previous work, we noted it's decreasing. So if it's bounded below and it's decreasing, that tells us it's convergent. Okay. There's other ways of proving that it's definitely bounded below. I'm not going to worry about that though. Let's look at. I think that'll do it. Let's just leave it at that. And, okay, so the completeness axiom, you might want to look at that thing in the book, but I think that's a pretty good idea of what's going on. Okay, thanks for watching.